Hello and welcome to this week's What Were They Thinking? Among the variety of news items we have for you this week, unexpected and, in some ways, not surprising consequences of taking glucagon-like peptides or similar weight loss drugs. The science that can destroy about 99% of cancer cells, in a laboratory setting only. Ghostly creatures seen in the deep ocean, and, well, they're creepy, as you would expect, with a description of ghostly-like. Lost rules to one of the most ancient board games to ever exist, and, of course, the bizarre publication by Nature regarding the lack of existence of probability. The timestamps for these and other news items can be found in the description box below. Let's start with something really dumb. Claims that the COVID-19 vaccine can alter your DNA. No. Just no. But in the longer version of no, the first issue we have is that you will, to a certain extent, have either RNA or DNA-based vaccines. There are a handful of basically antigen-generated type 1s, but they're primarily Chinese, and most of the world hasn't used them because they're kind of shit. So we have RNA and we have DNA. Now, in terms of the RNA, nothing can be done there. The human body, for the most part, lacks the facilities to reverse RNA into DNA. So we can ignore those for the most part. And the few exceptions that do exist are largely irrelevant for this conversation. DNA, which would be theoretically what needs to be incorporated into DNA, would be the other possibility. But you need something that would not only allow the DNA to incorporate, but incorporate effectively and still be able to be expressed. And this is missing. Not just missing in a vague sense, but missing in its entirety in any and every instance of these vaccines. And no, there is no naturally occurring version in the human body. Your cells don't make this. Your cells don't need to make it and never have. On occasion, viruses will, because they need to incorporate into your DNA to be replicated, but unless you have a very weird, very specific set of circumstances in which you have both concomitant viral infection and somehow the virus has incorporated part of the vaccine into its genome, it's not going to happen. You can see how this is a problem. But you might be wondering, why all the claims of it happening then? And it's pretty straightforward. There's been the discovery of spike proteins in blood years after vaccination. It's something that wouldn't be that surprising if somebody had, say, for instance, been infected by COVID-19. Yeah. The argument from the nutters and conspiracy theorists is that antibody tests have proven these people weren't infected. But antibody tests, first of all, aren't that reliable, not in this context, partly because it relies on users to use them correctly, that the antibody tests be current for the current version of COVID-19 that's circulating, and to be stored correctly amongst a bunch of other considerations. If you want to be sure that somebody has been infected, PCR testing is the only way to be certain. Yeah. Why these idiots jump straight not only to the most convoluted, complicated, and utterly impossible answer, when there is a very simple, very realistic answer available, is mind-boggling. But we've never accused them of being deep thinkers, just very deep in shit. In terms of things that are slightly less predictable, we have weight loss drugs, and particularly in this case glucagon-like peptides, resulting in a reduction in muscle and bone mass. Now, in some respects, this is unexpected. In other ways, it's actually very much an obvious outcome. In fact, it should be one of the most predictable outcomes. We say this latter point for a very straightforward reason. The less you eat, the less you're going to be taking in things like calcium, you're going to be taking in the various other minerals needed for your bones, the various amino acids and similar to get protein, and so on and so forth. And so, naturally, you're not going to be adding mass to it, because your body's going to be sitting there thinking, I'm starving, I need to pull out all the resources I have in storage to make sure I maintain my current state, which is typically going to be overweight if not obese. Therefore, the use of these drugs, it's kind of obvious what would happen. Now yes, the other alternative is that something more significant is going on here. And that is slightly more noteworthy, because if it is a more significant scenario than just a reduction in dietary intake, leading to a significant reduction in other parts of the body during its natural response to what it considers a stressor, then yes, this could be noteworthy. It could being said with a massive asterisk next to it. The simple reality, though, is it's more likely to be the former than the latter. The reason it's likely to be the former is that, by its very nature, people are taking this medication in its various forms in order to lose weight. The human body takes a rather dim view of trying to lose weight. Essentially, when you are fat, it's meant to be a case of, oh crap, we're suddenly in a famine or a drought, there's no food, there's no water, what can I make use of to be able to survive? Your fat stores. Now, the moment you reach a certain tipping point in the usage of this, particularly in the case of a sudden and significant decrease in calorie intake, such as that occurring due to these drugs, you initiate what is essentially a survival response of sorts. That survival response is, okay, the body will break down as little of that fat as possible, and instead it will look at other things, like muscles, or in this case bone as well, in order to maximize what it can, let's say, use and the benefits, while minimizing the chances of you dying from starvation right away. It's one of the big issues around things like people who have been starving for a long time trying to recover. We're not going to go into great detail here, just understand that this is actually, in some respects, a very predictable outcome if you suddenly go from 0 to 100 in your weight loss journey. You'll find a video linked in the top right of more detail around issues to do with starvation and how the medical community has learned how to deal with this. In somewhat more useful news, particularly if you work as a beacon of Gondor and you light up the world every time the sun hits your head, your chromosome may well be able to grow back its hair.
Emotional damage!
Enough jokes about bald people, but it is a treatment for baldness. Maybe. It's some more challenges in that respect, but the idea is that if you have hereditary pattern baldness, which is arguably the most common in both males and females, there is a new line of research, let's call it, using deoxyribose part of, sugars, essentially the D in DNA. You could theoretically help the body regrow hair. Now, the use of sugar to regrow hair might sound really odd, but hear us out and then judge for yourself, and possibly judge us for making bald jokes, as they may come out anyway. It's just something about that shiny, slippery, oiled surface that you just can't quite hold off for very long. The challenge you're going to face with this research, and one of the reasons why we say it's very early, is that for the most part it's entirely been proofed in a rodent model. Essentially they took a whole bunch of mice, shaved them bald and then waxed them, and waited to see how well the hair would grow back after they applied a sugar-based gel. Over 20 days there was a fairly substantial result. To be clear about it, it's not perfect, but it's damn good. And certainly better than the other options on the market at the moment. There are basically two options if you're not going to go down this pathway. The first is minoxidil, and it's not entirely perfect. In fact, it's largely ineffective in a lot of cases. The other is a prescription drug called finasteride, which affects the testosterone conversion in adult males, but isn't available for females. However, in terms of the males, it leads to things like erectile dysfunction, breast pain, testicular pain, reduced libido, and depression. The very things that, bald people were trying to avoid in the first place, most likely. There's very few reasons to worry about having a full head of hair other than wanting to have sex. If, and this is the big if here, the deoxyribose gel proves just as effective in humans, it could be used not just to treat hereditary pattern baldness. In fact, there's a wide area of things that it could be used for. For example, the effect on hair as a result of chemotherapy. There's things like alopecia. There are all sorts of conditions that could be at least cosmetically treated with this. But on the other hand, it could also lead to a huge drop in the wig industry, as all those toupees suddenly lose their meaning, and all those companies that are making them suddenly have no market. Or alternatively, that market is picked up by the very same people who are working in it, who are now so stressed their hair falls out. This could in fact become a vicious, self-fulfilling cycle. In news that's slightly more useful, at least immediately useful, research that can kill just about every cancer cell it's used against. But it involves two considerations. One, it's only workable in a laboratory, and second, it vibrates the molecules to death. The fundamental study design looks at taking aminocyanine molecules and then hitting them with infrared light. Now, the molecules themselves, once exposed to infrared light, begin to vibrate and jump around with a lot of force and with a lot of energy. And the idea is, once you do this, you can break apart the membrane of the cancer cells, which sounds like a good solution. The problem here is probably going to be pretty obvious though. That is, you need cancer cells in isolation, which isn't necessarily an option. Most cancer is not growing in a petri dish, it's growing inside a human. And because of that, getting it out is a problem. In fact, in most cases, once it's out of the human, you don't really care anymore. So you'd have to be able to use this technology in situ, and that's probably not going to happen for a very long time yet. The second is going to be delivery. Specifically, delivering those particular aminocyanine molecules only to cancer cells. In fact, we'd argue this would be a situation in which things like, say, antibody-based delivery of drugs is the ideal solution. The ability to deliver them using an antibody that binds only to the cancer cell, then shine your near-infrared light on it, and suddenly only those cancer cells will die. There is one immediate kind of obvious drawback though, and that is infrared light could possibly, and understand it depends on dose, exposure, time, etc., cause more cancer cells, because you're damaging various parts of the DNA, particularly thymine, which can become twisted, let's say, and this can lead to all sorts of problems with the DNA strand. But for now, let's assume that, at least in theory, what they've called basically a molecular jackhammer works as intended, where intended. This could be an incredibly effective way of reducing tumor size and theoretically gradually breaking down or removing a tumor without massive damage to the human that's being treated. Rather than having to, say, go in surgically, cut out a massive tumor, you instead deliver a limited dose of this chemical. You then treat the site with the near-infrared light, and you reduce the tumor mass. You repeat this several times until the tumor either shrinks, or, in the best case scenario, is gone entirely. But again, that is being incredibly hopeful. And next we have a sort of archaeology and animal studies crossover. It's a almost perfectly preserved baby mammoth found in Siberian permafrost. Now, this might be a rather, let's say, a disquieting image, particularly if you're a fan of Ice Age, but it does mean, theoretically, we have a almost perfectly preserved sample of a 50,000-year-old female mammoth. For now, all we really know about it is that it's thought to be a bit over a year old, weigh at about 180 kilograms or just under 400 pounds, and is about 4 feet or 120 centimeters tall, and about 200 centimeters or just under 7 feet long. Another thing we can look at with this is, theoretically, if, and there's a massive if to this, the tissues are well preserved enough, we might be able to extract DNA from it. And if we can extract DNA, we might theoretically, and again this is a very, very tenuous statement, be able to not necessarily conserve the species, but at least get a better idea of what's going on with them. In something we know nothing about, and we discover ever more that's terrifying, you have the deep dark ocean. And literally, we're now at the level in the ocean where basically no light ever penetrates unless you're either in a submersible or in a submersible that's about to implode. In this case, we're fortunately in the former, and what you see if you're down that high is creepy jellyfish-like things. We don't know what else to call them. They look kind of like a jellyfish, but they're not. The reason you can see this bizarre ephemeral creature is that it has bioluminescence. That is, it glows of its own accord. The other option, of course, is that the researchers have been confused and mistaken a plastic trash bag for an animal in the deep dark ocean. After all, it's entirely possible. It's why plastic bags are not pretty. They're turtle killers, or at least so says John Oliver. And, well, his word is not always the most reliable, but, well, the black and white toucan is at least occasionally entertaining. In this case, at least, it's unlikely to be plastic bags in the deep dark ocean. Partly because of that whole bioluminescence thing, but also partly due to the sheer number. About 157 different examples or individuals of the species were observed. That means there'd have to be a lot of plastic bags down there, and the chances of that many being that deep in that small an area over that time frame, not really great. Plus the other observed phenomena, particularly with its relationship to other species that we know do live just at a much shallower depth. Next we have what is arguably a bad science, but bad science for all the wrong reasons. In this case, it's an article claiming that the world's longest burning bulb could outlive us all, and, well, they're not wrong about the headline. But the key thing here is that the headline doesn't capture the whole story. This bulb does not produce much light. Let's be clear about it. It does burn. It does burn basically forever, or at least it has since when it was first made in the 19th century. However, the bulb itself doesn't produce enough light to actually be useful. And there's the key. Just about all of the currently available bulbs will have a much better light production percentage or capacity than this does. But, as a consequence, they are burnt out that much quicker. It's a trade-off between performance and longevity. To use a very crude analogy, you could drive your car at, say, 1 kilometer an hour, and you would theoretically get much better fuel efficiency, but it would take you a ridiculously long time to get anywhere. Or you could drive at 100 kilometers an hour. You would get there very fast, but you would burn a lot of fuel in doing so. You can see how you need to find an appropriate tipping point between efficiency and longevity. And not just that, the other consideration here is that this is, for all intents and purposes, an incandescent bulb. Essentially a glass bulb with a wire filament inside of it, in this case it's carbon, but close enough for this purpose, and ideally an inert gas. Now, any glass thin enough to actually be useful in this context is fundamentally going to be very delicate, so it will easily break, whether it's from extreme changes in temperature, mishandling, just general wear and tear. It will fail eventually. By contrast, an LED bulb, ideally, and understand there's some variation in this, will be far more resilient to wear and tear along with any other brute force approach you take to it. But they are somewhat more susceptible to heat as well. Despite that, they can last anywhere between 50,000 and 100,000 hours in an ideal scenario. There's again some variability based on quality, manufacturing, design, etc, etc, etc. But still, there is a good reason why, although this ancient running bulb could theoretically outlive us all, it's not actually an improvement in many respects. In what isn't an improvement in many respects, we have ancient rules, and we now may understand how the game is played because we have those rules at long last. It's an ancient board game found in Shah-e Sokhta in Iran. It was dug up in 1977 and nobody's really known how do you play this game. We have a board, we have pieces, but no idea what to actually do. It's like if you're playing different versions of Uno. Are you allowed to play a reverse on top of a reverse? Can you stack +2s? Can you stack a +4? Is a skippable? And so on. But in this case, given how ancient the game is, it's actually a lot harder because you can't just go to the manufacturer and check what their official rules are. This is distinct but similar in some respects to the game of which we do at least know somewhat more about. Fortunately, now we have at least found some rules to tell us what happens. Some, but not all. We say some, but not all, as they're more or less trying to create derivative rule sets that seem to make sense based on the player pieces and the board itself. And they do have relatively contemporaneous board games to use for that purpose, so theoretically, this does make sense. And once they've taken actual players, taught them how to play and let them go for, they seem to be reasonably happy across the board, although, then again, depending on whether or not these were graduate students, the temptation to tell your supervisor, no, this is shit, may not ever actually happen. So, yeah, take this with a lot of salt, or, given that it was found in Iran, maybe a lot of sand? Last we have the weird, we'll call it article, or it's more like a blog post from Nature, which is titled, Why Probably Doesn't Exist, but It Is Useful to Act Like It Does. Yeah. Just take this quote as the initial premise of the entire article. That is, And yet, any numerical probability, I will argue, whether in a scientific paper, as part of weather forecasts, predicting the outcome of a sports competition, or quantifying a health risk, is not an objective property of the world, but a construction based on personal or collective judgments and often doubtful assumptions. Furthermore, in most circumstances, it is not even estimating some underlying true quantity. Probability, indeed, can only rarely be said to exist at all. No, again, this entire article is sort of putting the cart before the horse, if you will. Science requires some fundamental premise on which we can measure things. Now, as a rule, all science operates on 3 assumptions. That is, we exist, that we can measure things, and that we can make changes to the universe, which we can then take number 2, and measure what we've changed. Now, it's an assumption, but an assumption that we all more or less accept is reality. And so, we must, if we're able to measure something, be able to make a judgment on whether or not that thing is actually a thing. So, yeah, we do indeed have a probability. Now, can we extract that probability out beyond the current situation and the data set we have? Well, that's what statistics are for. In fact, that is the fundamental issue we have with the entire article. It effectively says that even though you can state there is a probability of something occurring, it's either a binary outcome, that is, it's either a 0 or a 1. It will or it won't. For example, even if the probability is 70%, for example with rain, it either will rain or it won't. Now, the fact is, you are making that derivative value, that is that percentage of something occurring, on actual real-world data. That is things we can measure and observe directly. Now from that, we can then make a reasonable, and understand it's a reasonable inference of outcomes, which is the key thing here. And as the article itself notes, until the event itself occurs, or somebody is able to directly measure it or be able to observe it, it is always that. It is an unknown. We can only make what is at best a well-informed and educated guess on the likelihood of an event occurring, which is a very different matter to knowing what an outcome is. This is almost on par in some ways with the nature of, let's say, intelligent design, creationism to make it more simple. That is, creationists argue that because we already have a definitive and known outcome, that is, humans as they are, there is no possible way for the universe to have created us. Well, no, that's because we know the outcome. We know what the probability is. If we were to instead look at this the other way around, that is, if we know that there is one thing at this very start of time, and this one thing can start splitting off and forking and becoming multiple other things, what is the probability that one of those forks will eventually be humanity? But we don't need to know that. All we need to know is that it is a possibility. And therein lies the core difference between what they're talking about, subjectivity, which is based on a known outcome, and an unknown outcome and the likelihood of what we're talking about being that outcome. It's a weird tangent for nature to go down, as we never expected them to become creationists, but that seems to be what it is that they're spouting, which is truly bizarre and really disappointing. That's all the news we have for you this week. Thank you for watching. If you found it interesting, consider liking, sharing, and subscribing, and please do post any comments, questions, or suggestions you have below.